Hey guys, welcome back to my series on restoring classic late 40s American black and white electrostatic televisions. In this series I'm going to be pointing out some of the differences between these sets and the more common magnetically deflected sets, give you some tips, some tricks, some suggestions, some pitfalls to avoid to get these up and running. Alright, we are in the home stretch. We've got the set working rather well. What I'd like to talk about in this segment is some modifications we can make to the set. Alright, we are in the home stretch. We have the set working rather well. I want to talk about two topics in this installment. One is taking a look at how some other electrostatic sets do the horizontal and vertical deflection, and then some modifications we might want to make to our electrostatic set. So I've been focusing mostly on the Admiral and Motorola because they are so common, but they also share a rather interesting circuit innovation that lowered the tube count that a lot of other electrostatic sets do not use. So this is a Hallicrafters T54, which I bet a lot of you are familiar with. A rather collectible, interesting, unique design, kind of a cool set. Well, they did their deflection in a very straightforward manner, but it requires a lot of tubes. So here's the vertical on the top, horizontal on the bottom. Both use a multi-vibrator oscillator that requires two triodes. Classic circuit. You can make it with transistors, you can make it with tubes. It consists of a feedback circuit. Lots of little oscillator projects use them. Classic design. But the output of that is not going to drive our deflection plates. We need it to be much larger in amplitude. We need two waveforms 180 degrees out of phase to feed to the deflection plates. One way to do it is to use two more triodes and configure it with phase inverter, so you get a capacitor and a couple of resistors feeding the plate of one into the grid of the other, and then they get coupled. These are those high voltage caps going to our deflection plate. So two triodes oscillator, two triodes for push-pull output. Horizontal, same deal, just smaller values. So here we have 0.01, here we have 100 picofarads, but same type circuit, two triodes multi-vibrator, two triodes for the output. Okay, that's how Hallicrafters did it. Let's look at Teletone, another very common, very popular set. They use this chassis in a number of other brands as well, like Mech, for example, an automatic. Same deal. Two triodes vertical multi-vibrator, two triodes push-pull output, two triodes multi-vibrator, two triodes output. Alright, let's look at an Emerson. We stored one of these a while ago. Neat little set. They did it a little bit differently. Vertical vibrator, multi-vibrator is the same deal, and then two on the output. But for this horizontal oscillator, you have two triodes, but for the output, they made use of a 25L6 driving a specialized coil that would do the phase inversion. So yeah, there's two ways to step it up and do the phase inversion. You can just do it all with tubes, or you can use a transformer. Pros and cons to both. I think you get better linearity and more control if you use tubes versus transformers. Because transformers need to be specially wound, and I think you're going to lose some of the detail because transformers aren't perfect. They're not going to couple it perfectly, but it worked well enough for Emerson, so that's what they went with. Now let's contrast these to how Motorola and Admiral did it. Alright, first the vertical. Both Admiral and Motorola figured out a way to use a single triode for the vertical oscillator because they use a blocking transformer So rather than having a multi-vibrator with two triodes, two active elements, they used a transformer for feedback and a single triode. And then we get our push-pull output. And the Motorola is very similar. We've got a single triode and 6SL7 dual triode push-pull output. Okay, well, what about the horizontal? Down there in the corner, that's it. A single triode. How in the world did they go from 4 triodes to 1 triode? Well, one thing, 2 transformers. And the other is a very, very clever bit of engineering, and Motorola did the same thing. Single triode, 2 transformers. One of them is a blocking oscillator, and the other is the output to do the phase inversion and amplification, sort of. Now, I'm going to borrow somebody's work from another website. I will give him credit right now and give you a link to it. Dr. Holden did a great write-up on the circuit and has it published on his website. This saves me from having to break out the whiteboard and draw diagrams because he did an excellent job with them. So this is our goal. We want sawtooths to feed to the deflection plates, and we need 180 degree out of phase. This ideally should be perfectly vertical, but you can't do that. You can't instantaneously switch several hundred volts. There's a little bit of a retrace time there, but as long as you keep it quite short, 9.5 microseconds, you're fine. And then, of course, we've got our ramp. And 450 volts out. Now, our little Admiral set only runs on 250 volts. So we got to step that up. And the same with the Motorola sets. The sets that use direct drive have, one of them, I think the Eliminator has a tripler in it. And it makes the power supply is much more elaborate, and it has a much higher plate voltage to get that output. But Admiral Motorola didn't. So how do you get 450 volts out when you only have a 250 volt supply? Well, transformer. So there's our blocking oscillator with the transformer and our triode, so that'll get it oscillating, and then this will step it up and do the phase inversion. So we have half of it in the cathode circuit, half of it in the plate circuit, so we get the inverted output and we couple it to the plates. Okay, but it's not that simple, because you're not going to get a great sawtooth out of just doing a blocking oscillator. Think of it this way. I'm oversimplifying things quite a bit here, but easiest oscillator you can make would be like a Colpitts type oscillator, and you get a sine wave out. You get a coil and a capacitor, resonant frequency, an active element with feedback to keep it going, and you get a single frequency out that's a nice clean sine wave, as we see in the picture down here. But we don't want a sine wave, we want a sawtooth. But what these clever engineers realized is, hey, take a closer look at a sine wave. A portion of it, around where it crosses the 0 line, is rather linear. And if we just take a portion of it and ignore the rest of the sine wave, hey, there's our nice linear ramp. If we could just take a portion of that and reset the oscillator and have it restart again. So it wants to make a sine wave, and they figured out a frequency of 2 kilohertz was a good one to choose. But the output frequency is more like 16 kilohertz. So they're just taking 1/8 of this whole waveform. The trick is to get it to start and then stop when you want it to. And it has to synchronize to the incoming pulse. So that's where the magic is with these carefully chosen capacitors and resistors, and you trim it with the horizontal hold and all that. That has to do with starting it when you want it to start and stopping it when you want it to stop. But that's how they were able to do it. They made a sine wave oscillator, but they don't let it do what it wants to do. They stop it and restart it for 1/8 of the time instead of letting it go through the full sine wave. That was the magic, and that's how they were able to come up with this very creative circuit and reduce the tube count considerably. So why didn't any of their competitors use it? I'm not sure. I do know that Motorola was one of the earliest electrostatic sets on the market, and it proved to be quite popular. Admiral was early, but not quite as early. The Motorola came out in late 47, and Admiral not till 48. I don't know if Admiral licensed it from anybody. I don't know if the original circuit is patented or copyrighted. Mr. Holden went through and he researched who came up with it. And he does waveforms and pokes around. I came up with Photo and White. I think they were issued patents in England on this. I have seen this circuit mentioned in some Sam's PhotoFact tutorial. It might be in Grob's Basic Television. So I don't know who exactly invented it in the States. If they licensed it from Photo and White, I'm not entirely sure. But they certainly got a patent for it in England, and they described how the circuit operates. So kudos to them for coming up with a very creative circuit. But most manufacturers did not use it. So I don't know if they didn't want to pay licensing, or they just wanted to do it their own way and use their in-house design, or they thought their circuit worked better. I don't know. But there you go. Now, if you're wondering how well does this work, it works rather well. Maybe it doesn't have quite as good linearity as some of the other designs, and if these transformers are bad, you're really out of luck because it's not an off-the-shelf part. That might have been one of the reasons other manufacturers didn't. Maybe they couldn't get these transformers. The Motorola one looks rather, they both look a little odd, so maybe they had to make them themselves and the other manufacturers didn't have the resources to do it. Could be part of it. I don't know. Alright, let's switch gears and talk about retrace lines. This is especially important these days because most of us are working with tired 7JP4s. I imagine when these sets were new, same with magnetically deflected sets, when you get that super bright phosphor, you can turn the brightness and contrast settings so you really never see retrace lines. But as they get tired and you turn up that brightness, you start seeing them. What's a retrace line? It's as the electron beam paints the screen left to right, top to bottom. It gets to the bottom and it has to go back up to the top to paint the next frame. When it goes back up, the horizontal oscillator is going as it's shooting back up and you get a zigzag on the screen. Now it's only there briefly, it's only there for the vertical retrace interval, so it's going fast, but when you turn that brightness up, the phosphor persistence is enough that you start seeing it. So we want to blank it out. Now Motorola did add retrace blanking. I think they're the only ones who did in their TS18, which is what this is. But the TS18A, like final revision, they added retrace blanking. But most of these sets, the Admiral, the Motorola, the grid, the control grid, pin 3 here just gets grounded. And the cathode goes to the brightness control and the video. This sets the DC offset, and then the video is AC coupled, and that's it. So the modification is to break that ground connection. Instead of grounding the grid, you pick a signal off of the vertical output and use a small value capacitor and a resistor to turn that large sawtooth into a little blip during the vertical retrace interval, and you couple it to the grid, and that will blank out your retrace. These values and that design came from the Motorola TS18A late design. And in most sets you can add this modification rather easily. So we're going to add this to the Admiral. You have to find that wire going from pin 3 to the chassis, disconnect it from ground, find this output, pin 5 in particular on this design and add in these two components. I don't think you need to go quite as high as 1000 picofarad, but remember that is a bit of a large spike there on that vertical output, so I would use at least 500. 1000 is not a bad idea if you've got one. I don't think it's critical as a value. You could use a cheapo like Z5U type ceramic cap there, because we're not looking for if the value varies a little bit with temperature or something like that. It's not going to be a big deal. We just want to make a pulse. All right, that's the easy modification. Now here's one that's a little bit more complicated. And that is DC restoration. So I just mentioned how the brightness control sets the DC offset level, and then the picture information is AC coupled. Problem with that is AC coupling the video signal means you lose the reference level, like the background brightness level. And it's really noticeable on some of these electrostatic sets that when you go from a dark scene to a bright scene, the background is just washed out gray, and I find myself constantly reaching to the knobs to tweak the brightness and contrast. It's because the black level is just floating around. It's not clamped to something. It's typically called DC restoration, but in the circuit, he labeled it as a clamper circuit, and this is also done by Mr. Holden. There's a few ways to do it. I've seen a number of designs. This is a pretty straightforward way to do it. So most of these parts are just stock in the Admiral set. There's our peaking coil, and there's our coupling cap going to the picture tube. To clamp it, he adds some resistors, a capacitor, but the key thing are these two parts. It's a sample and hold circuit. So this diode only conducts during, I believe the way it was set up, it only conducts during the blanking interval, during sync pulse, because the sync pulse is a good reference level. The bottom of that, the sync pulse, that's a fixed reference level in the NTSC video standards. And this holds that value, so you get that sync pulse and you got all your video information. You want to capture that sync pulse level and hold it during the whole vertical drawing of a line so you get to the next sync pulse. So you want to choose a capacitor value here that's large enough that it can hold the charge for that line, but also small enough that you can charge it fully during that sync interval. So that's the challenge to choosing the parts. And this diode, you don't want to use just any diode. If you were to use like a 1N4007 power diode, those are meant for running on power supplies, 60 hertz, 120 hertz. This is running at about 16 kilohertz. So you want a diode that can switch quickly. You want a switching diode. But if you use something like a 1N914, 1N4148, those are originally for computers. They only have like a 50 volt voltage PIV on them. So you might want to go with a Schottky diode that can handle a few hundred volts, which I believe is what that is. But that's what it comes down to, is you want to sample that sync level and hold it while the video is being displayed and feed that back in. So that sets our DC level. However, you still want to have a brightness control. So this is sampling, it's holding, and it's mixing that level in with the brightness control and using it as a DC level coupled to the AC video signal. Does that all make sense to you? I hope it does. Now before we make any changes, let's see if we can actually illustrate these problems. So let's do the retrace first off. As I say, this is a pretty strong 7JP4, so we don't see them, but if I go with the brightness, these streaks going through, and I have the contrast all the way down. If I turn it up enough, they start going away, but if I go too high, I'm overloading the sync circuits and the picture starts to go wonky. So if you had a set with a weaker picture tube, you would need to have the brightness up more like this, and it'd be really obvious. So the modification, those should go away. Well, let's adjust it so everything's looking pretty good. And then let's see what happens when the scene changes, like we go to commercials or something like that, and see if we can illustrate the other problem. I think I can illustrate the problem really well on this because we're in a dark scene. It's way too bright. I'm starting to see retrace lines. It's washed out, so we got to drop the brightness. And now it's too dark. And put the brightness back up. Seems to be especially bad when you go from an inside dim scene to an outside bright scene. You really have to tinker with it. It's still looking kind of too dark. Put a little bit more with the brightness. Just notice when they get out of their vehicles and we had a bright band up here with the sky, it made the lower part look especially dark. It's starting to look a little too bright and washed out. Another thing is when you tune your setup really well and you put in all fresh tubes and you're feeding in a strong signal, it can really be a bit much for the set. So I have the contrast all the way down, and that's how I've done it, had it set from most of these demonstrations. If I go higher with the contrast, it gets too harsh and I start losing sync and it gets really overdriven. So you might want to decrease your input level to the set, use an attenuator on it. And then now it's looking washed out. It's a little too bright because the whole scene, and we're seeing retrace lines, so you drop the brightness down. You drive yourself nuts. And it doesn't help that the brightness control's on the back of the set and rather inaccessible. So why didn't they add DC restoration back then? Well, you need a diode, you need a capacitor, and a few other parts. A diode means adding a tube and a tube socket and more wiring, and adjust my horizontal hole. And you need to add a capacitor, and then added labor costs. So it would add several dollars to the cost of the set, so they'd leave it out. Now it's getting too dark, so they got to increase the brightness. Okay, there you can see it's really bad. We got a bright band up here. I can't see anything down here. It's just black. Increase the brightness. Hey, there's actually a field and cars driving around. That's the issue. You need to constantly tinker with this level. Alright, so we want to find the grid, which is pin 3. And if you look on the base of this particular CRT socket, they're numbered, and it's the orange wire. So if we follow that around, it goes through a hole in the bottom of the chassis, comes out here, and it's connected bottom of this tube socket right there. So we need to disconnect that. And then we gotta look around to find this. We need pin 5 of the 6SL7, which is that guy right here. It's nearby. And then we're going to need to find somewhere to connect up that capacitor, a resistor, and that wire. A spare terminal lug would be fantastic. I don't suppose we have one. Actually, do we? Yeah, we do. It's a little out of the way though, but the terminal strip up here has an open terminal right in the middle. We could possibly use that. But it would mean running this wire somehow from here over to there, which is a bit far. It'd be better if we could use this terminal strip down here, but I don't see any openings on it. So what we can do probably is just do it in free space. So there's a ground lug here. We can use the ground on the tube base. And I mean, it's not like there aren't other parts that are connected in space with wires going to them in this set the way they did in the factory, like this guy right here, or the two peaking coils and the cap over here. So it's sort of in keeping with the spirit of how it was made. So let's dig up some parts first and disconnect that wire and see what we can do. Now, I don't expect there to be enough slack on the CRT wire that you can reroute it. You very likely will need to splice in an extension. I needed to add about that much length to it. It got me over here, so I used a 270 picofarad 1000 volt cap. I happen to have a bunch of these on hand. It's type X5 ceramic dielectric, 270 picofarad 1000 volts, and a 220K resistor. Grounded it right about where that orange wire used to be attached. Join the two together here, put some heat shrink over the ends so I won't bump into anything, and then connected my orange wire right to there. So let's flip the set down and see if it had any effect. Alrighty, sets it back on. Was it successful? Well, let's crank up that brightness. Up all the way. I don't see any retrace lines. Down, up. Let's check out the contrast. All the way down right now. Let's turn it up. Turn up the brightness. Moving both controls. Min, max. No retrace lines. I would say that was a successful modification. Now let's see about that DC clamp, DC restoration modification. Now I'm just going to tack these modifications in for now so we can judge the results. If I like what I see, I'll do a more permanent job. Some of these are quite easy to add to the existing circuit. For example, this half microfarad 350 volt cap goes from the wiper of the brightness control to ground. And one leg of that pot is already grounded. So here's that brightness pot. These days, no reason to use an electrolytic for that. We can get a half microfarad plastic film cap. It's a 400 volt polyester film cap. It'll work just fine. Going from the center wiper to the ground lug. Now that center wiper, then we need to, it goes to a 470K resistor that's existing in the circuit. Need to put a diode just right across that existing resistor. After a bit of tinkering, I realized it was easier to leave the wire going to the CRT and the 0.05 or 0.047 cap installed and the wire going to the brightness control installed, and modify that the components going between the two. So instead of just a 470K, here's our 470K with the diode and the new 47K. So the bottom here with the stripe and this outer one, those go to those two lugs with the stripe towards the bottom. I'll have to finagle it in there. And then this center lead, that needs to go to capacitor, 0.1 microfarad in series with a 10K resistor, and that all needs to go over to the video amp over here to pick off what I presume is the, yeah, it's the sync pulse. Alrighty, there we go. Let's flip the chassis down and give it a try. So we just went from inside to outside. Still looks fine. I presume those balloons were against the bright sky, whereas before when we had the sky, bright sky at the top, the bottom was just black. You couldn't even see what was down there. So I'm thinking this was a successful modification. Now I'll leave it up to you if you want to go this far, because yeah, it's not the original design anymore. You're tinkering with it a bit more. I do recommend the Retrace modification in any set, be it magnetic or electrostatic, if you can do it. DC restoration, if it's not too intrusive and you don't mind modifying things a little bit, you might want to try it. In this case, it does seem to have improved things quite a bit. Alright, there you have it. That is going to be it for this installment. Hope you enjoyed it. Thanks for watching.